Good morning, students. Today we are going to see the second unit recap. So, in the second unit, we have seen the fundamentals of probability theory and statistical inference. What the probability theory states: probability theory is a branch of mathematics that deals with quantifying uncertainty. It provides a framework for analyzing the likelihood of different outcomes in an experiment or a process. So first of all, you know already what is probability. So let's say you have a tossed coin. So head or toss. So the 50% probability, right? It provides, this theory provides a framework for analyzing the likelihood of different outcomes in an experiment or a process. So tossing a coin, you have two output, but in a real process, we have a different outcomes. So analyzing the likelihood of different outcomes in an experiment or a process is about talking about the probability theory. So the probability theory and statistical inference are essential in chemical engineering for data analysis, process optimization, quality control, and risk assessment. These concepts help engineers make improved informed decisions when dealing with uncertainties in chemical process. So the experiment, for example, any process or activity with an uncertain outcome, measuring the purity of chemical bar. So the sample space, the set of all possible outcomes of an experiment, the purity of chemical product could be any value between 90 and 100%. The event, a subset of sample space representing the specific outcome of interest. So for example, the event purity is above 95%, include all values from 95% to 100%. So what is my event supposed to occur? So the sample space may be between 90 to 100 or maybe even less also, but the event which need to be occurred is supposed to be between 95% to 100% that purity. So the fundamentals, first of all, we need to understand the probability theory and the statistical inference, which will help you to know about, understand the, what you call it, essential in chemical engineers for data analysis, process optimization, and quality control. Okay. So probability, the probability has been defined as the number of favorable outcomes divided by total number of possible outcomes. So this I already told you in while taking the subject, this particular part. Okay, the classical probability, empirical probability, and subjective probability. There are different types of probabilities are there. What are they? So with an example we have already seen extensively. So I just skip this part. Please try to understand. These are the probabilities which are available. So I would like to highlight mainly on empirical probability, estimating the probability of a pump failure based on the past data. So is a data, empirical data, okay, empirical probability based on the experimental data. Okay, so non-empirical equation, okay, we say actually based on the theory. Okay, empirical equation or empirical formula or empirical probability talks about the experimental. Empirical means experimental. Please don't forget this one. So you will have a confusion between the empirical and non-empirical. Empirical means experimental data. Okay, or experimental derived equation from the experimental data. That is an empirical equation. Okay, so usually the empirical equation need not be unit consistent. Okay, that you need to know. But non-empirical equation comes from the basic principles of a theory will have a unit consistent. Okay, that I would like to highlight here. And coming to the probability distribution in chemical engineering, discrete distribution, binomial distribution, and Poisson distribution. Continuous distribution. So under the continuous distribution, for measurable outcome, you have a normal distribution and exponential distribution. So this type of distribution we already discussed enormously in an extensive way. So I just move on to the next one, statistical inference. So in the statistical inference involves drawing conclusion about a population based on a sample. It helps in making prediction, estimating parameters, and testing the hypothesis. So for example, population versus sample. What is population? The entire set of data points, all reactors in a chemical plant. A subset is a subset of the population, 5 randomly chosen reactors for analysis. Estimation, point estimation, interval estimation. Point estimation talks about single value estimate of population parameter, the average reaction yield in a chemical plant. So it's a point estimation, the average reaction yield. Interval estimation, a range within which the true parameter value lies. Example, 95% confidence interval for the heat transfer coefficient in a distillation column. So what are the hypothesis testing? Null hypothesis, alternative hypothesis. So the null hypothesis, no effect or no difference. Alternative hypothesis indicates an effect or difference. For example, dependent variable and independent variable just take. So the independent variable like pressure, temperature, concentration of reactant. The dependent variable is a product concentration, that is a output concentration, that is a yield or a reaction yield or the output or outcomes. Okay, so in that case, if the temperature and pressure does not have any effect on the output, that means output concentration, that is a product concentration. Obviously, we say is a null hypothesis. No effect on the or no difference between the effect of the temperature and pressure. If there is any effect, then we need to take as an alternative hypothesis. Once null hypothesis is rejected, we will accept the alternative hypothesis. This you might have studied actually in maths, right? So which we already discussed earlier. What is the different types of regression analysis that are available? Regression analysis, multivariate regression, okay, multiple variables like pressure, temperature and flow rate, and application of chemical engineering regarding the probability theory, okay, the quality control, process optimization, reliability analysis and environmental monitoring. Quality control, using quality control chart to monitor the process variability. Example, monitoring the pH values in a wastewater treatment plant. Process optimization, using probability distribution to optimize the reaction condition. Example is finding optimal temperature and pressure for maximum yield. Reliability analysis, estimating the failure probabilities of equipment. So reliable. Example, predicting the lifespan of a distillation column tower. So estimating the failure probabilities of equipment is coming under the reliability analysis. The example has been given here. Environmental monitoring, using statistical inference to analyze the pollution level. So the example is estimating the probability of exceeding air quality standards. So regarding the probability theory, I would like to conclude the probability theory and statistical inference provide powerful tools for chemical engineers to analyze the uncertainty, okay, optimize the process and make data-driven decisions. These concepts are crucial for process design, safety as well as to have high efficiency in chemical industries. Coming to the second part, okay, the parametric and non-parametric of unit statistical test under unit 2. Hypothesis testing and confidence intervals are essential in chemical engineering for what? For process control, quality assurance and experimental analysis. These statistical methods help engineers make decisions based on the sample data, ensuring that conclusions are reliable and applicable to real world scenarios. So what is the difference between parametric and non-parametric test? Assume that the data follows as known probability distribution, that is a parametric test. Do not assume a specific distribution and are useful for non-normally distributed data. Then we go for a non-parametric test. So assume the data follows a probability distribution, does not follow the assumed specific distribution, then go for the non-parametric test. In statistics, non-normally distributed data refers to data that does not follow the normal distribution, that is a Gaussian distribution. While taking the subject, I told you about the marks which has been obtained by the students supposed to be a normal distribution. Is to not be what you call the data may be skewed, have heavy tails or contain outliers, okay, which is characterized by a bell-shaped curve. So that's for example, the normal distribution A plus B or something supposed to be at the normal value B, C and all. When you have U, C as well, sorry, U, C and that's supposed to be lower case. That means number of failures supposed to be less, number of absentees supposed to be less, withdrawal case supposed to be less, and the number of C, that depends. Okay, either it may be at the lower end or at the middle range. So when you have O and A plus supposed to be at the skewed at the lower range. Okay, not many students supposed to get a O. That doesn't mean that thing. Usually when you conduct the when you have a class mark distribution, usually it will automatically will form in a normal distribution, that is a Gaussian distribution. There are some cases like in lab where many people will get O grade because that conducting an experiment is a hands-on experience. So mostly the students will do better when compared to the theory exam. Okay, the lab experiment they will try to score better. So in that case we could not follow the normal distribution anything. However, the O grade will not be that much grade, supposed to be higher than A plus, yeah, I mean B grade or something. Okay, so meaning to say not all students will not be skewed at one point. Okay, so please try to understand the thing. So why I'm trying to say, give an example, you're supposed to know how the mark result analysis has been carried out. Okay, in the result analysis will be carried out. Okay, in any institute, is not need not be necessarily our institute, maybe any institute. Okay, so the characteristic of non-normal data, skewed distribution, heavy tails, bimodal or multimodal distribution. So bimodal or multimodal distribution, multiple peaks in the data, presence of outliers, large deviations from the mean. So the characteristic of non-normal data has been divided into four categories: skewed distribution, heavy tails, bimodal or multimodal distribution, presence of outliers. When you see the common causes in chemical engineering, so parametric and non-parametric common causes in chemical engineering, reaction kinetics, some chemical reaction rate do not follow a normal distribution due to complex reaction mechanism. So non-parametric test or non-normal distribution where you could be able to see in reaction kinetics. Experiment failure rate often followed an exponential or billboard distribution rather than normal distribution. Exponential is a non-linear. Okay, so that type of distribution will be there in the equipment failure rate example in chemical engineering. Particle size distribution, log normal distribution. So what are the assumptions they made in the parametric test and non-parametric? So parametric test is a normal distribution, no assumption about distribution in a non-parametric test. The example for testing the parametric data, the test data is t-test, ANOVA, analysis of variance, regression, whereas non-parametric test, Mann-Whitney U-test and Kruskal-Wallis test. Okay, so more powerful when assumptions are met, more robust for small and skewed data sets, non-parametric, so the efficiency wise. And coming to the parametric statistical test, we have t-test and we have paired t-test, analysis of variance. Under the analysis of variance, we have one-way ANOVA, two-way ANOVA, regression analysis. Under the regression analysis, again it has been categorized as linear regression and multiple regression. Non-parametric test comes under Mann-Whitney U-test, Wilcoxon-Sain rank test. So a non-parametric alternative to the t-test, a non-parametric alternative to the t-test used when comparing the two independent groups. Example, comparing the viscosity of two polymer samples when data is not normally distributed. Okay, so Wilcoxon-Sain rank test is coming under a non-parametric alternative test, alternative to the paired t-test. Okay, so that one is a t-test, is a paired t-test, is an alternative used for different data. Okay, the previous one is when comparing with the two independent groups. Okay, so the example for Wilcoxon-Sain rank test is example comparing impurity levels in wastewater before and after treatment process. So then we need to go for a paired t-test. So you should know actually when we need to go for a parametric test or non-parametric statistical test, under which one is we need to choose, whether we need to go for a Mann-Whitney test or Wilcoxon-Sain rank test. What is the similar alternative for this type of non-parametric test compared to the parametric test that has been given here. Okay, and compared to the Kruskal-Wallis test, the alternative is ANOVA in a parametric method. Here they comparing the three different solvent extraction for metal recovery. Then we need to go for Kruskal-Wallis test, Spearman rank correlation test. Okay, so non-parametric alternative to Pearson correlation. Okay, alternative to Pearson correlation used for rank data. So the example they have given for Spearman's rank correlation is that examining the correlation between the catalyst surface area and the reaction rate when data is skewed. When you have SQ data, the correlation, examining the correlation between the catalyst surface area and the reaction rate. When the catalyst surface area is large, reaction rate will be more. When there is no, you could go for a correlation between these two when the data is skewed. So in that case, we can go for a Spearman rank correlation. Okay. Hope you understood this one. So confidence of interval, which we have already studied that part. So what is the application of this parametric and non-parametric test for hypothesis? Okay, in process optimization, quality control, equipment reliability, environmental analysis, even all the process, okay, data analysis and statistical analysis, what else? So all the things which we are talking about process optimization, very simple. Okay, what for we are doing actually data analytics and machine learning everything to have a process optimization. Okay, and make the process very simpler. Okay, and then from the data, real-time data, we could able to optimize the process proactively. Okay, that is very important. Proactively or else in a reactive manner. Okay, so conclusion: the parametric tests are powerful when assumptions hold, but non-parametric tests provide flexibility for non-normal data. Both are crucial in chemical engineering for analyzing the process efficiency, ensures quality control, and making data-driven decisions. This we have already discussed. Okay, so now we are moving to the regression analysis. So a regression analysis is a statistical technique used to develop a mathematical models that describe the relationship between these variables. Predict outcomes, if it helps engineers to predict outcomes, optimize the process, and understand how changes in the input variables affect the output variables. Regression analysis is a statistical technique to model the relationship between the dependent and independent variables. It helps in predicting outcomes, understanding trends, and making data-driven decisions. In a simple form, regression aims to answer how does one variable affect the other variable changes, whether there is an interaction or not interaction. Okay, can we use past data to predict the future values? So that is the main objective answer to the simpler form of regression, aim to answer only these two questions. Coming to the significance of regression analysis, prediction and forecasting, process optimization, identifying the key influential factors, and decision making and policy formulation, understanding the relationship between the variables. Very important. One variable how it affect the other variables because of the interaction effect, okay, or synergetic effect, how the output variables is going to affect. This all need to be studied. Hope you understood. Regression is a powerful tool for modeling, prediction, and decision making. By understanding the relationship between the variables, regression helps in improving the process, optimizing the efficiency, and making the informed predictions across various industries. Now we will see what is linear regression. Okay, linear regression y is equal to a plus bx plus epsilon. Epsilon is the error term. So is y is equal to mx plus c form is a linear regression. So when you have a linear relationship between the variables and the independent variables and dependent variables, the relationship is linear, then we can go for a linear regression. Multiple linear regression, as I told you, you have multiple variables like x1, x2, xn. So how this affect the response variable, that is y, or you can say is a dependent variable. Non-linear regression, most of the chemical engineering processes leads to a non-linear relationship between the variables, that is a dependent and independent variables. So in that case, we can go for non-linear regression. Polynomial regression, okay, it may be a quadratic effect or a polynomial effect, that is x power 3 and x power 4. Logistic regression and rich lasso regression and partial least square regression. So partial least square regression is useful when independent variables are highly correlated, okay, such as in multi-component chemical process, and even partial least square regression, which will help you partial least square thing which we are talking about in the evening previous videos, okay, regarding how the output has been directly correlated with spectroscopic analysis, right? Okay, so hope you just correlate that one. Okay, multicollinearity occurs when two or more independent variables in a regression model are highly correlated, okay, with each other. So multicollinearity occurs when two or more independent variables in a regression model are highly correlated. Let's say you have temperature and pressure. When you have increased the temperature, it does having a pressure effect also. Okay. So independent variables in a regression model are highly correlated. PV is equal to nRT. When the pressure increases, the temperature is also increases, right? So PV is equal to nRT for ideal gas law. So it's something which will correlate. Okay, the independent variables sometimes will positively correlated. So one will increase the other effect. Okay, that we need to know. One variable at a time in a design of experiments. Okay, which will not have this issue because we are just changing only one variable. Okay, and coming to the logistic regression example, quality control in chemical manufacturing. In a pharmaceutical plant, the tablets are classified as acceptable or not acceptable, which is coming under a logistic regression. And coming to the region lasso regression model, modeling the catalytic performance in a chemical reactor. Let's say you have temperature, pressure, reactant concentration, flow rate as a independent variable. So the catalytic reactor efficiency is a dependent variable. So these variables may be highly correlated. Ridge regression helps prevent overfitting while keeping all variables in the model. And partial least square regression. So in pharmaceutical industries, spectroscopic techniques, which I told you just now, okay, this method has been used. And coming to the example for regression analysis. So here they have given modeling heat exchanger that we already discussed, and kinetic modeling of a chemical reactor using non-linear, very important. Rate of reaction is equal to Ernst Laetla, K is equal to A into E power E naught. E naught is the activation energy. Okay, divided by RT. RT is the temperature, R is the universal gas constant, where capital C and W is nothing but reactant concentration and catalyst loading respectively, where M and N or N and M are to be estimated. Okay, so the non-linear model helps determine the reaction kinetics, optimize the reaction conditions. So it's a non-linear relationship and improve the catalyst efficiency. When you see the third one, distillation column, you will have a quadratic regression. I mean a polynomial. Quadratic is x power 2. Okay, a polynomial regression is developed, and the variables like R, that is reflex ratio, except with the feed composition, boil-up rate, are individually correlated. I mean with the coefficient you could be able to see, and it also have a quadratic effect, that is square R square x square and v square. So regression analysis is an essential tool in chemical engineering, for predicting the process outcomes, optimizing the performance, and improving the efficiency. Different regression techniques like linear, non-linear, and polynomial and logistic are used depending on the complexity of the process. So regarding the design of experiments, I will take as a separate video because it's a second part of the recap of Unit 2 that I will cover in next video shortly. Thank you for your time. Thank you for your attention. If you have any doubt before the exam, just please come and knock me. We will clarify. I will ready to clarify your doubts. Okay, with the suitable examples. Okay, so you are very well can contact me at any time on face-to-face section or else during your free time. Thank you for your attention.